myself also. I can do it. All right.
I get that, yeah.
Let me. All right. So thank you all for coming. I'm going to be talking about latent space approach for modeling exchangeable multinetwork data. So first, I'm going to begin with some terminology. So recall that a network is just a collection of interconnected entities or actors. So they are usually represented with graphs where vertices are the actors or entities in the network, and edges represent the corresponding ties or connections. So depending on the kind of edges we are working with, we can classify networks as being directed if edges have an implicit directionality in the network, or we can classify them as undirected if this directionality doesn't exist. So networks can also be classified as weighted or unweighted, depending on whether or not edges are equipped with a non-negative number describing the relations. So in this way, a network dataset is basically composed of a set of nodes, some nodal variables describing these nodes, and also a dyadic variable describing the relations. Something really important to say here is that when we are working with networks, in at least real-world networks, the dyadic variables tend to be correlated. Let's think about social networks. If we are working with social networks, relations between nodes with similar characteristics tend to be stronger or more likely to happen than relations of nodes with different characteristics. So, and in this way, if you are in a social network, then you are more likely to be linked with someone that is friend with you, with a friend of a friend, or with someone who is similar to you in a sensible way. So in this way, every single model approach we consider to model networks should take into account these dependencies, and in order to be a good abstraction of the data generating process. So in this work, we're going to keep it simple, and we're going to work with undirected binary networks, and which means that we're going to basically work with symmetric Saussure matrices, which are just regular square matrices whose entries are 1 or 0 depending on whether or not the edges are connected. So a subtlety here, when we work with Saussure matrices, we tend to represent them from bottom left to top right. So now I'm going to talk about the data we're going to be working with and the model we considered in this project. So this kind of data is called cognitive social structure data, CSS for short, and it is basically a collection of relational statements between all pairs of actors in a system. So it is usually denoted with Y subscript I prime, J, where I is the sender of the relation, I prime is the receiver of the relation, and J is the perceiver of the relation. So you can think about CSS data basically has a set of J networks where J is the number of perceivers in the system, and over a common set of I actors. So in summary, you're going to have J networks with square adjacency matrices having size I by I. So the data we considered is data coming from Krafthart in 1987, where the management personnel in a company in the US were interviewed about how they perceived the relationships within the company. So here, the dyadic variables are defined as 1 if executives J thinks that that executives I and I prime are friends. And so we see that we're going to work with an undirected relation. And we also have available some nodal information. So we have the corporate level. So we have the president, 4 vice presidents, and 15 managers. We have available the department membership, so we have 4 departments, and the president doesn't belong to any department. And we have the tenure time, so we have the length of service at the company. So in summary, we have a set of 21 undirected binary networks over a common set of 21 executives, actors, and at one point every actor has a observer in the entire CSS, and with the attribute information P, which is just the information I just talked about. So here I'm showing 3 selected networks of the system. The one corresponding to the president, and the ones corresponding to 2 managers in department 2 and 1 respectively. And also, here I would like to talk about a couple of characteristics. The first one is that we can perceive some variability across all the networks in the system. So here you see, for example, that the president is perceiving a lot of relations, but the other managers are perceiving just a couple of relations. For example, actor 3 is perceiving just a couple of relations in his own department. And the other thing is that even though we have a lot of variability across networks, there are also some commonalities. So for example, you see that the president is perceiving all the relations that actor 3 is also perceiving, and the president is also perceiving some relations that actor 17 himself is perceiving as well. So we have, even though we have variability, we also have commonalities across networks. So this kind of data have been mainly analyzed using descriptive measures and or even models, but independently. So other approach that is quite popular.
Clarification: the perceiver is a star.
No, every single executive in the company is a perceiver. So this is the network corresponding to the president when the president was the perceiver, and this is the network.
And who's the president?
The star. The star.
The star is always the president.
The star is always the president.
Yeah, you need something. You need in the empty box something that says star, president, circle, okay, director, square, executive.
All right.
Or whatever it is.
So here the perceiver is the president. Here the perceiver is actor 3, which is this general manager. Right. Here the perceiver is actor 17, which is another general manager over here. Okay. So the other approach I was talking about is an approach in which you compress all the information in a single network. So this is called a consensus network, where you're going to have a link between 2 actors if more than half of the executives in the company think that they are friends. So what we are pursuing here is a model that allows us to describe the data generating process jointly, using all the information across networks. So this is going to allow us to generate shrinkage estimators that are going to borrow information across networks, and that is going to help us to improve estimation and prediction, for example. So now I'm going to talk about in detail about the model. So before gathering any data, because we are working with undirected networks, then the symmetry in each adjacency matrix is strongly suggesting that these matrices are row and column exchangeable. So basically, what we are saying is that labels in rows and columns are carrying no information, and we can think also about the matrices themselves as being exchangeable in the full collection. So under this consideration, we formulate a probit model in which the dyadic variables are modeled in terms of a new auxiliary variable Z, which independently is going to assign 1 or 0 depending on whether or not this auxiliary variable is greater than 0. And in order to introduce covariation and the latent effects, then we're going to model as in a regular probit model, we're going to model the auxiliary variable in terms of a linear predictor which is including P covariates, and is going to describe the relational patterns associated with the nodal variables. And also, we're going to include a bilinear effect, which is going to describe all the relational patterns that are not described by the linear predictor. So the bilinear effect, you can think of this effect as a regular interaction effect between the latent or unobserved characteristics of all the nodes in the network. And what it's something really important to note here is that we are embedding these latent characteristics in a k-dimensional space. So now, once we've modeled the auxiliary variables, we are going to also consider a distribution for the latent effects. And what is important to note here is that these latent effects are going to be normally distributed, but we are allowing the latent effects to have an actor-specific mean effect across all the networks in the system. And as a standard choice, we are going to consider independent conjugate priors for the model. So under this setting, what we have is that the interaction probabilities that we're going to denote with theta I prime j are going to be, as in the standard probability model, a function, the CDBF of a standard nodal distribution evaluated at the mean of the auxiliary variable. And the dyadic variables are going to be conditional independent with a Bernoulli distribution. So this is the general formulation we consider in this project. And before showing you the results we got for the cracked data, I would like to discuss a couple of issues that arises with the model. But before, let me tell you, we have that the unknown quantities include the auxiliary variables, the covariance coefficients, latent variables, the mean effects, and the variance. So we implemented a regular GIF sampler to approximate this posterior distribution with a standard updates. So we have a truncated normal for the auxiliary variables, we have multivariate normals for the latent variable, the covariance coefficients, and the mean effects, and an inverse gamma for the variance. So the issues I wanted to describe about the model. The first one is the issue of anti-identifiability. So because we are working with bilinear effects, then we have that any rotation or reflection of these latent effects are going to keep the bilinear products invariant, as you can see here. So what does this mean? This means that if we rotate all the latent variables according to the same transformation, to the same rotation or reflection, then we're going to have that the likelihood is going to remain invariant. And basically this is a problem because we can't properly identify the latent characteristics. So what we do, we do the standard thing, we force identifiability, and what we do is that we put all the latent characteristics with respect to the same point of reference. So we choose a target configuration, which I call yield subscript 0, that in our calculations we select to be the first value of the mean effects after the born period. And then we are sampling, when we are sampling the latent effects, what we do is that we take these latent characteristics and then we put everything with respect to this same point of reference. So, and then we make inference over these rotated, transformed characteristics. The other issue is that because the latent characteristics are embedded in a k-dimensional space, then we have somehow to select k. So how do we do that? Basically, it depends on the goal of your analysis. If your goal for analysis is merely descriptive, then you can choose k to be just 2 or 3, and then you're going to get a really nice representation of the social dynamics of the system. But if your purpose is going beyond description, then you somehow need to select K with an improper method. So we went with the usual thing, and we worked with likelihood-based measures of fit that are going to help us to assess the model fit versus the complexity of the model. So we have the standard measures. We have the AIC, we have the BIC, but the thing here is that if we treat all the parameters in the model has been fixed, then we probably are gonna overestimate the complexity of the model. So because we're working with a hierarchical model, then what we're gonna do is that we're gonna work with this DIC, which is the version for the formulation when we work with hierarchical models, and we implement all of those. Okay, so now I'm gonna show you the results we got from for the credit card data. First of all, I'm gonna talk about the prior elicitation. So we need to select the hyperparameters for the covariant coefficients. We need to select the parameters for the actor-specific mean effects and for the variance. So in the absence of prior information and before gathering any data, we expect that all the interaction probabilities follow an uniform distribution over the 0-1 interval. And also considering that the bilinear effects follow at least approximately a normal distribution, which is something natural to think because they involve a sum with more and more terms when the latent dimension increases. Then, in order to make the interaction probabilities to follow a uniform distribution, then we set the expected value of the bilinear effects to be 0 and the variance to be 1. So under this restriction, then we get these expressions, and these expressions have to be met in order to satisfy our expectations a priori, and then we get the following. So we get that all the mean effects have to be centered at 0. Then, because this inequality have to be met, we simply take the value of the variance to be just in the middle of the interval, and then we take this value for the variance of the mean effects. And then for the covariant coefficients, we do the usual. We center everything at 0, and then because we want a prior as flat as we can, we take a high variance. And then for the inverse gamma, we take a value of 2 for A, and then from this expression, we solve for V. And this is the prior specification you use in all our calculations. So using this prior specification, we first of all select the value of K, and we get that the BIC, the DIC, and the IC, I'm not showing that here, are saying that the best value that is balancing the model fit and the complexity of the model is 4. So we're going to use 4 for our calculations. So the first thing I want to show you is the results we got for the regression coefficients. So we consider 4 covariates. We consider an intercept. We consider a 2 binary covariates indicating whether or not 2 executives belong to the same department or have the same corporate level. And also, we consider the 4th covariate to be the difference in the tenure time. So something really cool about working with these kind of models is that you're going to get a measure of the impact of the covariates on the link formation across all the networks in the system. If you were using the consensus network, then you're not able to do that. So for example, if you take a look at the president, we see that for the president, when he is perceiving the relationships, having the same corporate level, being in the same department, and the tenure difference are not relative important factors when he is assessing these friendships. But if you take the general manager 9, for example, you see that for him, having the same level is not an important factor, but belonging to the same department is going to positively affect the probability of finding an interaction between 22 executives, and the same thing for the tenure, but this time doing it a negative. So these are the results for the covariant coefficients. Also, we can get estimations for the interaction probabilities. So the first row is the raw data, and these are the interaction probability matrices. And you see that we get a nice correspondence between the data and the interactions that as we were expecting. And something really important about working with these kind of models is that it is going to allow us to study the social dynamics of the system. So, and it's going to allow us to do that in several ways, in several dimensions. For example, if we are interested in how a given executive is perceiving all the relations in the system according to his own view, then you can plot what we call a Latent configuration within, and then you can see all the disposition, all the configuration of the executives according to a given view. But if you are interested in studying how a given executive is perceived across all the executives in the company, then you can plot what we call a Latent configuration across. So basically, you can see how a given executive, in this case the president, is perceived according to all the other perceptions. So you see, for example, here that vice presidents 2 and 21 are perceiving the president in a similar way. And if you need just a nice summary of what is going on, you can plot the actor-specific effects, mean effects, and then you can get a nice representation of what is going on in summary in general in the system. Additionally, we performed we wanted to evaluate the prediction, how our model does in terms of prediction, and we consider a 10-fold cross-validation experiment. And then what we did basically was that we plotted the true positive rate versus against the false positive rates. Then, in order to measure the predictive capabilities of our model, we took the area under the curve, and we considered 3 cases. So we consider a case using fitting our model with latent effects across all the system. We consider a case without latent effects across all the system. And we consider a case using latent effects, but fitting the model independently. So we see that when you do not consider latent effects, then the model is going to basically behave really poorly in terms of prediction. When you consider latent effects, even though if you do it individually, then the capabilities, the prediction capabilities of the model is going to improve. But definitely, when you consider the full structure and the latent effects, you're going to get the best. And we get around a 90% rate of prediction in terms of the areas under the curve. And finally, because we are claiming that our model is generating this data set, it's a good representation, a good abstraction of the data generating process. We wanted to see how our model does in terms of capturing important characteristics often seen in social networks. So one of them is the transitivity. So a friend of a friend is my friend. And then what we did is that we plotted the observed value that we get of the transitivity across all the networks. So we got the transitivity in all the networks, and then we computed the average. And we plotted the observed value of that. And then we generated a lot of data sets according to our models and the other models. And then we also computed the transitivity, and then we plotted the histograms. And we see that, for example, if we do not consider the latent effects, then we basically are missing this characteristic in the network. And basically, considering the latent effects, we are capturing this feature, but yeah, because in terms of prediction, considering the full consensus instead of doing individually, our model basically do the best job. So in the few minutes I have, I'm going to talk about the future work we are going to be doing. So in this case, we're going to keep working with multiple in a multiple network setting, but in this case we're going to consider other problem. We're going to face the problem of online social network integration. So as you know, many people around the world are spending a lot of time in social networks. So, and in turn, social networks are getting kind of specialized in some subjects. So, for example, people tend to share opinions in Twitter. Some people tend to share a photograph in Instagram. Some people tend to just look friends and family in Facebook. So, social networks are getting kind of preferred for some matters. So, what we want to do is that we want to somehow merge all these social networks, all these databases, in order to get a comprehensive single database matching all the records, all the profiles that correspond to the same person across all the networks, in all the social networks we are considering. So why is this important? This is important because it's going to give us, it's going to help us to create more comprehensive social databases. Also, it has a lot of practical applications because, for example, if you got a new cell phone, then we can develop automatic contacts merging, and also it's going to help us to analyze some privacy and online security issues. But even though this is really important, we also are going to face a lot of challenges. We're going to have high rates of overlapping. And this is a really big issue because people tend to have different names in their accounts. They tend to have different email accounts across their social networks. Even, sometimes they don't provide the same information across the networks. So identifying these individuals are going to be difficult. Also, even though it's forgiven in social networks, some people have more than one account per social network. So they use 2 different emails. So we want also to identify these individuals to be the same person. And also, this kind of data is going to be massive, so we're going to have an issue with that also. So really quickly, I'm going to show you the notation to understand the model. We're going to consider J undirected binary networks in the beginning. We're going to work first with in the undirected case. We're going to have records, so we're going to consider the profile information and the link information, which is something really, which is the novelty in this work, because we're going to exploit both the profile information that the user is providing, and we want to exploit also the link information, so the friends he has, in order to identify the same individuals across networks. And in our approach, we're going to also work with a latent method in which we're going to have the true profile information, which is unobserved, and a social space information. So basically, the idea behind all of this is that for a given social network, so for a given file with a given amount of records, we want to identify the records that correspond to the same latent individual. And we want to reconstruct, basically what we want to do is to reconstruct the link structure between all the networks and the latent population. So the model that we're going to consider is this one. So I'm going to go really quickly about this. We're going to keep modeling the dyadic variables in the same fashion as before with an auxiliary variable. But this time, we are going to consider the linkage, the linkage structure we are studying. We also are going to model the profile information in terms of the linkage structure and the distortion indicators. We are also going to model the latent characteristics of the population and the distortion probabilities. And finally, we're going to have the prior information. About this model, we have a lot of unknowns quantities. We could consider a regular Git sampler. That is going to take too long because it is going to compare it's going to go to all the records in the system. But we want to avoid that complexity, and we can consider two main approaches. We can consider the split merge MCMC. Through split and merges are going to accelerate this process that the GIF sampler is why the GIF sampler is getting behind. And we also we use blocking in order to compare records that have little distortion in some fields. And finally, once we are done with approximating this posterior distribution, the main goal is to estimate the overall linkage structure. So we want to identify the individuals that correspond to the same person across all the social networks. So basically, our main objective is to get an idea of how this linkage structure is behaving. So finally, we're going to consider a couple of extensions. So the two extensions we're going to consider is an scenario in which we have two kinds of networks, directed as a Twitter or undirected as Facebook. And also because the massive data we're going to be considering, then we're going to also consider some variational approximations in order to make things faster. And here, I'm showing the timeline for the projects. So this project is almost done, and we're going to start working on projects 2 and 3 right after this quarter. And thank you.
Fine?
Everyone.
That's fine. You guys go ahead. I do have a couple of comments.
Okay. So questions or comments?
No, so question.
All right.
You have Thanos in your committee.
All right.
So can you think of any other way of estimating K, the number of latent factors?
Okay, so we're talking about this. How do we select the number of dimensions in the dimensional space, right? The latent space. I think that when we considered the likelihood-based measures, that's a good way of doing it quickly. The link prediction was also given us the same answer, so 4. And the other thing is that these methods are kind of useful if we use if you don't use if you use just a small number of dimensions. It doesn't make any sense to use that many. So I think that for our purposes, it's enough. That's enough.
Yeah, but Pedro is trying to send you somewhere else. Pedro is trying to send you to an Indian buffer process.
Oh.
So any non-parametric extension where you actually try to learn K from the data.
From data. Okay, in a point I think that we thought about that, but
yeah,
in terms of the complexity,
that's the take-home message.
It doesn't work.
My experience is not very positive. Chelsea tried to do some of that, and she had a lot of visions. So. But he's trying to send you that way. So
okay.
he's trying to
I'm
make
going
you
to think of an answer then.
And there is an older version of that is to try to essentially put a prior on K and do reversible jump.
And try to
MCMC to try to learn K. So the other option is essentially to treat it as another random variable and put a prior on it, either directly by putting a prior and using Markov chain Monte Carlo to do computation, or indirectly by having a non-parametric process on a binary, on a set of binary matrices that is then used to essentially select whether the things are present or not.
But does the interpretation of each dimension changes if you have more different number of dimensions, or is always the same?
Oh, okay.
Like, right? Because you show the interpretation of the 2. So with 3 would the interpretation of the first 2 change when you have 3 dimensions?
Yeah, I think that when you keep adding dimensions and dimensions, then first of all, when you add more dimensions, then you're going to capture less and less variability across dimensions. So
yeah.
The interpretation of the dimensions, I don't know if that's quite simple if you use too many dimensions. And
but you said that the optimal number was 4, right?
Yeah.
And then you show the interpretability with 2. Like
yeah.
the interpretation was 2.
Okay.
You didn't show the interpretation with 4. Or
No. I'm using 2. Let me show you the plot and maybe I can express better my idea. Okay, I used 4 because I thought that that was the best choice in order to get good prediction estimation. And the advantage of using 2 is that we can get a nice graphical representation of what is going on with the social system. I think that we can get an interpretation in terms of the problem itself, in the sense that, for example, if you see this dimension here, the second dimension, then you see, for example, you can see it here as well, that the same color means the same department. So in a way, this, in some sense, this dimension is capturing something about the department membership. And maybe we can interpret the dimensions in a better way, but when you use 2 or 3, I think that maybe that's enough.
Going back to the question, those are the first 2 dimensions.
Yeah.
Okay.
No, just using another.
But
Okay, that's a good thing. So I
that
used 4, and then these plots correspond just to repeating all the model again, but just using 2.
Yeah, but you said that the best model.
Yeah, the best model in terms of prediction and estimation is gonna be 4.
Okay.
But if I just want a nice representation to show to people, then that this is 2. I'm not taking the first 2 dimensions of the previous field. No, I'm repeating everything with just K equal to.
Maybe you should just say.
Yeah, that's an important point.
But if you were to do that, the interpretation of the first 2 dimensions would not be the same as the one you have here, would it?
That's right. And the thing is that if I use 4, I'm not gonna use these 4 dimensions to make analysis of the social dynamics. I'm not gonna interpret those.
So you cannot interpret.
I'm gonna try to interpret
like
those 2 instead of the other 4. I'm just gonna get the other 4 in terms to get some nice predictions.
So basically, the interpretation changes if you have 4 itself.
Yeah, that's correct.
Okay.
Yeah, if you use 2, then just 2, then you're gonna try to capture all the variability in just.
So what's the interpretation of 4?
I haven't thought about that. I don't know.
So one way to try to deal with that is, you remember that we discussed about 2 different types of specification. One that basically has the variance of the use be constant across.
Oh yeah,
and the other one where the variance becomes smaller as you move. So one reason to do that decay in that way is precisely to try to ensure that the largest variability, it's like in principal components, that the first column corresponds to the largest variability of the data, and the second component has the largest. When you use a prior that essentially says that the variability a priori is the same on all of them, then you start getting in these issues of being harder to tell what happens when you move across dimensions.
Okay.
But
Okay, I see.
Now I have a practical question. How are you gonna? It's really cool the model like integrating information from all the social network. How are you gonna get those data?
Again.
How are you gonna get all those data from all those social networks? Like, what you have issues with privacy and.
Okay.
Because
So
you wanted,
you're talking about the future work, right?
Right.
Or the
Yeah, the future work, yeah.
Okay. So how are we gonna get data
like, and
for?
is it something that they would want to? Like, if I were Facebook, I wouldn't want someone to integrate my information with all the other social networks.
Okay. The first answer I have to that is that I've read like 3 papers trying to explore both the link information and the profile information, and I don't have the name of the guys here. I'm gonna do that in the future, but I got data from from previous papers and they got some profile information using we were discussing this today, the API. And so the answer is the following. We can get data from other previous research. And
so
also,
data from Facebook and from Twitter and from.
Yeah, and I also have them here available now because I emailed the others
So
and I
are they
said.
publicly available in general?
No. Now some privacy issues are implemented.
So the thing is, like, if you were able to create an app or something that was able to combine information of all the certain networks, right?
So that's
would you
one
actually
of
be able to do it? Like,
yeah,
it
that's
wouldn't
one of
be-
the reasons why this is useful in the following sense. Maybe you cannot access the profile information, but then you can use the link information to identify all the individuals in the across the networks. So then this has a technical name. I read about it, and then you can. What I'm trying to say is that you can use these kind of models in order to identify these individuals and see if they have failures in their security systems. So just based on the link information, then you are able to identify with some probability, with some uncertainty, some individuals across all the network, even though you don't have the profile information, and then you can see who corresponds to whom.
But the point is that you need to make sure that there is some sort of overlap between, because if you've got one subset of Facebook and one subset of Twitter, you may not necessarily have an overlap.
Yeah, but for example, if you have the case of the mobile devices in which you are a user, an egocentric kind of think about it. If you have you're a user and then you are providing all your accounts, then what you want to do is that identify all the individuals across networks that correspond to the same individual in a nice way. And that's an egocentric network.
You need to use the technical name of entity resolution.
Okay.
Especially given that Lisa is going to be there.
All right. And I need a better question and a better answer for your question.
And you're gonna you're just gonna spend a lot of time pre-processing data.
I honestly haven't thought about that. Yeah, but I think that's gonna be the case.
So in your first model, when you were showing the results for the transitivity, it looked like the individual model was better when you included latent, but you fit it for individuals and not.
Oh, okay, capturing the
Yeah.
the
So you do
transitivity.
better with individual. The most right model is this, right? Am I
Yeah,
correct?
this is the model
But the
without
one
latent
that-
models, but independently. But this is kind of in terms of the transitivity of the model. So I have two answers. The first one is that both are reasonable explanations for this statistic, but I didn't show this for time. I also have other statistics, and our model is doing much better in those statistics. So maybe I can.
That's fine.
All right.
Yeah, it's not so much about who
Yeah.
does better, it's about not doing too badly.
Right.
So as long as it is within,
Sure.
it's
I was
fine.
just, I thought you were saying in that slide that your model was like the best.
Okay.
Yeah. I don't know if I misheard that or
You
not.
can check into that. All right.
And the other question I have, so in your future work for your, is there so in your first model there was like a perceiver for each
Mhm.
network. Is there something similar to that in your future work? I wasn't able to follow.
No, the
No,
kind of
it's
data
just-
is totally different.
Yeah.
Here in the first case, we have a perceiver for every actor in the system was a perceiver of the relations. So here, no. So we have here different social networks, and then we're going to try to integrate all the records in a single database.
Well, but you could still think about Facebook as one perceiver
Yeah, something like
and
that.
Twitter as another perceiver.
And that would be
Oh,
okay.
notation of
Not
what
in
you
terms
described before.
of not in terms of users, but in terms of a system, for example. Okay, good.
So what happens in the first example is that the set of perceivers and the set of nodes is the same.
Mm-hmm.
And in the second case, it's not. So you have the set of nodes is the individuals using the system, and the perceivers are the companies that provide the social network service.
In the future work, it wasn't until you arrived to the end, it wasn't really clear what was one project and what was the other project. Like I understood that at the end, when you had the schematic, but
okay.
not while you were explaining it.
Okay.
Yeah,
So
the last
make
one's
sure-
a little bit compressed, but I'm not sure how to deal with that.
So make sure that
And
you could explain better.
So you had, I don't know, you had the model was the first project and extensions, right?
The first model was the
For your future work.
For
So
the
if
future
you
work,
look at here, right, you have project 1, that is the one that you are explaining,
Oh,
right?
yeah.
And then you have project 2 and project 3, but when you explain it, it all looks like the same project.
okay, yeah, I
I
see.
mean, but
Yeah,
I would
yeah, that's,
have
yeah, that's,
I knew the extensions were the third project.
yeah, that was my idea, that,
Okay.
the model was the second project and the extension.
Yeah.
So about the ROC, how did you deal with it? So
ROC, yeah.
I wasn't able to understand, do you, for the missing data, are you trying to predict only the network of the observer?
Okay, I understand your question. So, here, right? So, these ROC curves just correspond to the case of the latent effects and considering the entire cognitive social structure. So what we did is that we used the tenfold cross-validation, and then we assign randomly.
When you say tenfold of all the networks?
Yeah, for
or
all the
just
networks.
for the
So you're gonna get missing values in all the networks in the system. So more roughly 10 values or so for every network in the system. And then you train the data and then you predict it.
I guess the only comment is, I think that you could get rid of the slides with the predicted interaction probabilities, and I would bring back the slides with the descriptive analysis of the data. So it's a 1-for-1 swap. So remember that you have the box plots, because there are some things that I think you should highlight that you haven't. For example, the fact that when the perceiver, that perceivers are very different when they are perceiving their own relationships than when they are perceiving somebody else's.
They remove.
So there is a strong egocentric effect in the network.
So should I keep?
So I would keep that and instead get rid of the ones where you show the model field where you see the data in J case.
So it's better to have all the box plots and then.
Well, I put one, and you don't have to go into all the different metrics, but put one, for example, for degree. And then get rid of go back, I think it's one slide before this or two. Yeah. No, that one. Get rid of that one.
Okay.
Because, it's nice, but it doesn't really tell you.
In the one before this,
You could also get
I think you should do thicker lines if you have time.
Okay.
Yeah, and
Because,
if you have to get rid of something, this is probably the least interesting.
This one?
In some sense. Yeah, because this is just a regression.
I like that one. I like that one.
I would get rid of the sample, because who cares if it's a gift sample?
Also,
Or you're just sampling.
Oh yeah,
So this one.
yeah.
I mean,
Get rid of this one.
Yeah.
Okay.
By popular acclaim.
Okay. And include the box plots.
I just include
The
one of the box plots because I think that it makes
And if
sense.
you
Yeah, I
only
think
one
a
with
lot.
capital K equal to,
Uh-huh.
I would put in the
So here.
no, I would so I know that the first one is within, the second one is across,
So-
but see the second one, the labels and the main the first and the second one is exactly the same. Actor 7, press step 1. So if someone is not following or not, I don't know. I just would.
Okay.
yeah, just
Those
right.
look exactly the
Within-
same. Like looking like this, they look exactly the same, but with different.
And you should put across and within.
Okay.
Yeah.
I will do that. Yeah.
Just-
Yeah, that's definitely.
Yeah. I sincerely thought about it, but I was lazy and didn't do it.
No, I know. If you have time. If
When
not,
is your advancement again?
Monday.
Monday, okay.
Okay, let me see the one slide previous to this.
I don't think I've seen Tracy send out the announcement, did she?
Yeah.
yeah, she did.
She
She did
did
the
wrongly.
fence. She did the fence.
Yeah.
Oh, she
Yeah,
did the
that was
fence?
good.
That was
One was
awesome.
defending.
Oh, I didn't know. Okay.
Yeah.
Okay, I think we need to go. We have the new students
All right.
around, so we need
Thank
to
you.
go.
Oh,